Good afternoon and welcome to today's webinar on atomization improvements for additive manufacturing applications, sponsored by Praxair Surface Technologies and hosted by 3D Metal Printing Magazine. My name is Brad Coogan. I'm the editorial director at 3D Metal Printing, and I'm pleased to serve as your moderator for today's session. Before we get started, just a quick note about today's GoToMeeting session. It is being recorded for archiving. The recorded event will be posted to our website within the next few days. We'll let you know via email when that recorded webinar is available for viewing online. Also, I need to let you know that all the participants in this webinar are in listen-only mode. The speaker and other listeners will not be able to hear any audio from your site during the program. However, you do have the ability to communicate with us throughout the program by submitting your questions and comments using the question box, which is located in that right-hand control panel on your GoToMeeting screen. Simply type your question to an organizer as selected from the drop-down menu, and we'll pose your question to the presenter. You'll also use that same question panel to ask questions of our speakers at the end of the presentation. So now it's time to begin today's webinar on new atomization techniques and how they promise to improve the quality of 3D printed metal parts. Our speaker on this important topic is Joel Reichen. Joel is the powder plant manager at Praxair Surface Technologies. Joel has a PhD from Iowa State University in material science and engineering and specializes in the production of metal powders. He has published more than 30 articles and has authored 2 patents in the field of gas atomization of liquid metals. So please welcome Joel Reichen.
Thank you, Brad, and good afternoon to all the attendees who have called in. Thank you for your participation. As I move through these slides, we're going to make it fairly open to questions along the way. Please submit those questions to Brad, and I'd be happy to answer your questions as we're walking through this presentation. The goal of this presentation is to give you an overview of atomization techniques, how they're used for additive manufacturing products, and then how do we improve that along the way. So it is meant to be informative, and hopefully you do have questions along the way. So we're going to jump right in here. And first, I'm the powder plant manager here in our Indianapolis facility. This facility operates about 11 manufacturing cells and is in a large facility over 300,000 square feet. We've been making powders in excess of 50 years. What we specialize in is all types of powders, chemistry, shapes, sizes, and the facility is really broken down into 3 divisions. Those divisions are going to be metallics that come from our gas atomizers, and then our carbide division, which can be spray agglomerated, centered and crushed, and other types and varieties, and also oxide. So most of these are going to be spray agglomerated, fully dense and crushed, or some version thereof. We can modify all kinds of chemistries, and we'll get into that more in particular as we are in more specific nature as we move forward. So looking at the evolution of metal powders for additive manufacturing, really our business started in thermal spray equipment back in the 1950s. As that really evolved into coating services, there was a need for us to produce our own powders. This was meant for a competitive advantage. This was also meant to be a partnership with a lot of our customers, in particular customers in the aerospace marketplace. So they would come to us with challenges to develop new custom alloys that they could use for wear coatings and other types of coatings, corrosion resistance, and whatever they really need. We would work with them, with our engineers, and then come up with a process to produce those powders. When we started to look at our gas atomizers, we really expanded those gas atomizers in the 90s and early 2000s to meet the growing demand of thermal spray. Along the way, we found out that we could make a very spherical, highly dense powder and control the chemistry very well when it came to complex thermal spray alloys. That really was the base of our powder plant, and so having that core understanding of how to make powders made it a natural or easy migration into the additive manufacturing world. We maintain a clear understanding of how to make powders and how to engineer equipment to really maximize the yield and high quality that our customers demand from us today for additive manufactured powders. So So now that we know that really this technology, our powder plant, was evolved from the thermal spray business to the manufacturing of additive manufacturing powders, we wanted to talk a little bit about the metal powder characteristics for additive manufacturing. Of course, when we work with our customers, we get a lot of feedback. And one of the key characteristics that they're interested in is to make sure that the powder flows well. When we look at the flowability of powder, we always want to think about particle-to-particle friction. And so as the particle shape changes from spherical to irregular or faceted, you create more point contacts that can create increased amount of friction, which prevents the powders from sliding past each other. That can disrupt the flow. And so our customers want us to work together with them to understand how do we change the atomization characteristics and how do we change the physics of our atomization process to create more of a spherical morphology and eliminate surface defects. When you look at literature and read about powders, you'll hear things like satellite particles, which physically means a smaller particle essentially welded to a larger particle, looking like a satellite that's really frozen in place. It can also have dimples on the surface and irregular shapes. A lot of that comes back to how you're atomizing, the ratio of gas, that is, think of it as pounds of gas per minute versus pounds of liquid metal per minute. As we modify that, we can change the surface characteristics, we can change the surface the particle morphology, and we really specialize in that. So if we pour the metal hotter, we can maintain more spherical powders. If we control the recirculation of fine powders, we can prevent certain satellite fractions from rising up. And in doing so, we can really create great flowability. And that's what we're looking for in additive manufacturing. When we think about the size with our customers, those size ranges really change depending on the additive manufacturing or 3D printing equipment. So we work with a multitude of customers as well as equipment suppliers to maximize to understand what that yield needs to be and then maximize that yield for our customers. Maximizing the yield allows us to drive down cost, and it allows us to increase our volume. And we're seeing both of those play a key role as this market grows. When we talk about size, we always have to think about what happens to those powders that aren't in that size range. And I'm going to touch base on that as we move through this presentation. But in general, when we talk about size, we want to make sure we can control it well in terms of standard deviation, so we have less loss in terms of yield. We want to also make sure that it's repeatable. And I'm going to touch base on that when it comes to really our focus on productivity and repeatability in this plant, and how those are key metrics that you should be looking for when it comes to atomization technology. It's how repeatable of this type of technology is it? Or how repeatable can this technology be? So when you focus on size, in general, the laser powder bed technology requires a size range of less than 45 microns or 325 mesh, for those of you that are more familiar with mesh. It's very difficult to make that powder. Okay, it requires a clear understanding of supersonic gas structures. You also have to be able to handle liquid metal, and in the next slide we'll show some example of that. The next feature there is going to be, how do we control this? How do we control the chemistry when we melt? Do we understand what temperature do we need to go at, raise the melt pool to, in order to get very good control over the pourability or the fluidity of that liquid to feed it through an engineered nozzle? We also have to understand reactive elements. If we superheat too much, are we going to drive off certain reactive elements and therefore have too great a batch-to-batch variability for our customers to achieve repeatable results when they print this powder? We have, as I spoke to earlier, we need to control the morphology. Also, solidification rate. In many cases, we're now seeing customers that are asking for what we call metastable powders. So powders that are solidified at a rate that can lock in a certain key microstructure that they can't achieve using conventional casting techniques. And that's really another advantage of gas atomization. It is truly a rapid solidification process that allows us to achieve a microstructure that is can have certain properties that you can't achieve in using conventional casting because of its metastable nature. The next feature really is impurity level. How do we keep that impurity level low? Speaks to our melting recipes and our equipment. A lot of the impurities that are focused on with these new specifications focus on gas content, in particular oxygen and nitrogen. That gas content is derived from the atmosphere in which you melt under. It's derived from the raw material that you feed into your atomizer, as well as the reactivity of that liquid with the crucible that's holding the liquid, as well as the nozzle that you're pouring through. You have to make sure that there's compatibility with everything to make sure that you don't pick up these impurities. And so we'll talk about vacuum levels and how are they important, as well as gas purity that you're using to atomize with. Particle voids and satellites are going to be the next question. When we look at particle voids and satellites, as I spoke about, that surface defect concentration can affect flow. And so how do you control that? And we do specialize in making sure we create the optimum gas structure to not only prevent satellites, but to also prevent particle voids. And that has a lot to do with how the liquid is interacting with the gas. And we're going to show some examples of that using high-speed videos, as well as some schematics to talk through the interaction of liquid with high-pressure gas. But in general, this really speaks to the fact that we have to work with our customers, work with the OEMs of this type of equipment, so that we all understand the targets here. We understand the key characteristics that we need to achieve to make powders, I guess, work at the best level and the most repeatable level with this technology. So moving to the next slide, this is going to be slide number 5, and we're talking about the principles of fine powder production. I'm going to start to use the mouse now so that you can follow along. When we talk about the principles of fine powder production, you have to understand that there's 2 steps to make this type of powder. Step number 1 is primary atomization. That is, once you've created a liquid pool, you've superheated that liquid pot to an ideal temperature to achieve flowability and fluidity to make it to be able to transfer it through the nozzle. That liquid is now going to interact with the high pressure gas. So in general, we don't care how big your atomizer is. Melting capacity is something that we can scale up with basic chemical and mechanical engineering. The key part of gas atomization all lies within the knowledge base of understanding how to transfer that liquid through a nozzle, and then how to feed that liquid into a pre-engineered gas structure. That gas structure and the characteristics of that gas structure take many years to understand and develop the optimum gas structure to yield the correct droplet distribution for additive manufacturing. So as we feed the liquid through this nozzle, that liquid, as I move down to these figures below, that liquid's either going to free fall a given distance and then interact with the gas structure. In doing so, the gas loses a lot of its momentum, and so and therefore has less velocity when it strikes the liquid. And so you can think of it as the energy transfer is cut down by about an order of magnitude, and this process creates large droplets. So the only process taken advantage of here is really primary atomization, but very little, if any, secondary atomization. And that's where you make your fine powders. The powders that are less than 45 microns in diameter are, again, 325 mesh. When we go back to the schematic up here that was published by Uno back in 1989, really shows that as the liquid interacts with the gas structure, you can create a recirculation zone. And this is due to the high pressure gas zone that lies below the mock disk. And I'll show a schematic of that on the next page to better clarify what that means. But in general, the liquid is forced across what we call the landing of the nozzle. It has been sheared by this high velocity gas and broken into these primary droplets. You can think of it as it wets across the landing and it's first interacted by the gas, it creates this wave structure, and droplets are sheared off the top of this wave. That's why they would call this wave breakup model, again, published by Enigbo back in 1980. These large droplets can then be fed towards the center of the gas structure, and they are deaccelerated and then rapidly accelerated. And during that rapid acceleration, we call it secondary atomization. And what's happening there is the liquid droplet is now interacting with supersonic gas. And you can engineer these structures to operate at Mach 1, Mach 2, even in some cases Mach 3. And that velocity mismatch between the gas and the liquid really results in this microerosion. And so these larger droplets are being eroded as they're driven downstream. And this erosion product, or this micromist, is the finest droplets. That's going to be the droplets that are less than 45 microns in diameter. And how you can control that is really given by the gas to metal ratio, as well as your supersonic core length. There's got to be a balance there that has to be understood by your atomization engineer to create the most ideal distribution of droplets to maximize the yield of these powders. Moving on to slide 6, what we'll talk about here is gas structure. And so what we showed on the previous slide is really the difference between, and let me just back up one slide to confirm, is when you take advantage of both of these primary and secondary atomization techniques or phenomena, you're operating what we call a close-coupled mode. Close-coupled atomization means that the gas physically is closely coupled to the liquid. So as the liquid exits, it's immediately impinged upon by the gas. The other technique is called free-fall atomization. And in free-fall atomization, you're only going to take advantage of primary atomization. Therefore, you're limited to only making coarse powders. And also a distribution of that on the next slide or two. When we think about close-coupled atomization, remember that means that the liquid is immediately impinged upon by the gas. There's two different real styles or types of close-coupled atomization. First style is closed-wake atomization. In the closed-wake atomization, you've created a gas structure that actually closes its wake. Therefore, it forms this Mach disk. I'm not going to get into all the different shocks and the theory around a lot of this shock pattern, but it's important to understand that there is a Mach disk and that you're operating in this supersonic mode downstream. Below this Mach disk is a very high pressure zone. And so as the liquid falls out of this nozzle, it's going to be either pushed or pulled out of that nozzle depending on this gas structure. As it's pulled out of this nozzle by a type of aspiration or vacuum that's created on the tip, liquid will fall. As it strikes this Mach disk and breaks it up, this high pressure zone is released into what we call the shock bottle. This shock structure here represents the shock bottle, and as that high pressure zone enters this shock bottle, it'll force the liquid upwards where it strikes the landing of the nozzle, is wets across the nozzle and momentarily interrupts the flow of liquid. When that liquid flow is interrupted, this Mach disk has the ability to recreate this aspiration or suction on the tip of the nozzle, and the liquid starts to flow again. This all happens very rapidly, typically on the order of 35 hertz. And so if you watch the atomization happening in live speed, it'll create this flickering process. And if you know and understand how to control that flickering process, you can really gain an understanding of how you can control the distribution of those droplets. In comparison, you can operate in what's known as an open wake model. This open wake creates a constant suction and more of a stable atomization process in which you're consistently and constantly pulling liquid out of the nozzle, driving it downstream, and simply shearing that liquid with high velocity gas. But it doesn't go through the two stages of momentary shutoff. That momentary shutoff was really coined pulsatile atomization. And there are some very unique properties with pulsatile atomization that allows you to create ultra-fine powder with a very narrow size distribution to maximize your yield. This terminology was coined by Jason Ting back in 2002, and it was very interesting theory at the time. And we worked with Iowa State University and the Ames Laboratory, a division of the Department of Energy, to utilize high-speed cameras to actually verify that this mechanism is occurring. So we could actually use these high-speed videos to confirm that this mechanism is truly occurring. The advantage here, like I said, is that you're already making fine powder in the close-coupled format. But if you move to closed wake, you can shift by about a factor of 2 the average particle size. And so when you ever see a notation called D50, that represents by volume in general the amount of particles that are below that on average. So this is going to be your average particle size for an atomization heat. And so when we look at that distribution, where our average is at 26 microns and our standard deviation is very tight. In the open wake, we create coarser particles here. And so those are some just interesting terminologies to understand. And so what we're developing and understanding about is that if we use close coupled process and closed wake gas structure, we can create some of the finest powders with the most tight standard deviation, therefore maximizing our yield of powders within the range that our customers require for additive manufacturing. So looking at our atomization capabilities now, so we're going to move away from some of the theory and then more into some of the practice here. And so when we look at atomization capabilities, these are some pictures of our atomizers here in Indianapolis. We operate what we call our fleet of atomizers. We have 5 installed within the plant. We have 3 large atomizers that can melt up to 4,000 pounds per heat, and there is really some optimized technology around productivity that allow these systems to run all day, every day. And that's key to our massive throughput that we see here in the plant. We do have a medium-sized atomizer built for more of a pilot scale as we're ramping up from our developmental atomizer, which pours about 100 pounds per heat. And so we like to use that methodology when we work with our customers from really testing and developing to pilot stage to then ramping up to the hundreds of thousands of pounds onto our large atomizer. So in general, these atomizers can output a significant amount of liquid per year. In excess of 4 million pounds annually of liquid can be poured with this fleet of atomizers. And all of these atomizers operate in full vacuum, so we pull a full vacuum on them to get rid of all the air and other contaminants that are inside. Backfill with a high purity gas. Using high purity gas is very key to maintaining the highest quality of powders. So it reduces slag, therefore you can control your chemistry much more closely than melting in air. It also allows you to prevent oxidation during the atomization process. We use this technology for titanium-based, nickel-based, cobalt-based, and iron-based powders every day in this plant.
Hey, Joel, can I ask you a question here from one of the attendees?
Sure.
So he says, can the process be used to generate powders from other materials such as silica?
So to make more of a refractory type powder, Brad, I'm a little confused by the question. So
maybe Michael can, yes. Well, maybe Michael can rephrase with more detail. Let me ask you one other question, and I'll let you go ahead. So, with all the improvements, this is a question from the audience. With all the improvements, what's the yield of fine powder with particle size less than 45 microns? And then the follow-up question. So, what's the yield of fine powder with particle size less than 45 microns? And the second question is, theoretically, I can see the yield of fine powder could be around 70%. So why is the current rate so low?
So what I can say there is that when we look at yields, of course they're going to be optimized based on our customers' requirements. One of the keys is not to push the particle size too fine, because we do understand with additive there's typically what we call the bottom cut, so the lowest amount of particle size range that they'll accept in these machines. And typically that's between 10 and 20 microns, somewhere in there, and on average around 16 microns. Then we want to control the upper end of that size range distribution, which could be about 53 to 45 micron range. And so if we think about it holistically, on average, we're going to look at trying to maximize a yield of 45 on 16. We don't typically disclose our yields per se, but we do have some experimental data out there that we're willing to show that with this type of technology, you can maintain yields around 70% within that range if you know what you're doing and if you've engineered it correctly. And the key then is to maximize your repeatability. Use productivity tools. so that you create standardization and repeatability on the shop floor. That's something that I can't tell you enough, that without a solid productivity program and quality program, repeatability is difficult with these large pieces of equipment. And so again, if you back up, you have to engineer it correctly. You can then maximize your yields. When you think of about 70% yield, that is far beyond what others can achieve with different types of technology. So I would bet that close coupled closed wake atomization is really the most optimum method to be used to create additive manufacturing powders. I hope that answered the question, Brad.
We'll find out if there's a follow-up question.
Okay.
All right, so go ahead.
So when we look at AM metal powder atomization process, we want to break it down into several components. Batch, batch process, we want to look at elemental versus ingot. You want to select your raw material input stock so that it's most ideal for what the customer needs. So starting for elemental or pre-alloyed powder, ingot, as well as revert powder. So powder that can be remelted after atomized is another option that we can take advantage of. When we talk about melting, we want to be able to melt this powder in vacuum. So that drives out, as I said, all the air, and instead of using a blanket material, which means blanket simply means you're melting in air, but you're basically using a cover gas like argon to prevent the metal within the pot from oxidizing during the process. Pouring, we take advantage of tilt pouring rather, because really you can control the flowability of the liquid metal during the process much more in a much more controlled manner. And in controlling your metal flow rate really leads you to controlling your gas to metal ratio, which will yield the highest quality powder as you move forward. When we atomize then, we want to look at the metal stream droplets. When we talk about this, we want to look at gas. What gas are we going to select? When we look at the gas that we're selecting, it can be argon or nitrogen. In some cases, it can be air or water. And so when we look at that, when you use argon, you can create highly spherical droplets that maintain a very spherical nature. When you choose something like nitrogen, you're going to pick up a lot of nitrogen along the way. And some people use water. Water actually solidifies the liquid too quickly and doesn't allow it time to spheridize as it free falls through the chamber. And so you got to think of it as when you start with liquid and it's falling downward, you're allowing physics, that is surface tension, to create a spherical droplet. And then you want that droplet to freeze. If you freeze it too quickly, it can actually be irregular and therefore not flow very well within these additive machines. And as I mentioned before and talked about, we do maintain a close coupled technology. The last step is really to collect these solidified powders, and then we're going to go size them and size them using mechanical sizing and different air classification techniques that I'm not sure we'll get into today, but those are very important steps as well. We talk about, we're going to switch gears a little bit to our newest production cell and our newest technology, and that's titanium atomization. Titanium atomization offers many challenges, and there's ceramic challenges, meaning that as you melt titanium, you can't use traditional refractory crucibles. It eats into that crucible. It can actually break out of that crucible, and it contaminates the liquid very quickly. So you use a special crucible, and that's a water-cooled copper crucible. This would be kind of a water-cooled copper crucible example. When you use that, it's a very clean melting technology, but it prevents you from adding superheat to the liquid. Therefore, you have to really be careful about how quickly you strike that liquid with gas. If you don't add enough superheats, for example down here, and you use the close coupled technology, you're going to freeze that liquid out right away, and that's what we call nozzle freeze-ups. And then you have to start over. You have to go in, remove the metal, reload it. It becomes quite a pain and very low productivity. What Praxair developed and operates is really a proprietary nozzle. So this proprietary nozzle is designed to superheat the liquid titanium very rapidly. In a fraction of a second, it can add superheat coming out of this water-cooled copper crucible that allows the liquid to be atomized using this close coupled technology. This is a very big breakthrough for the industry. It's really the first commercial size titanium atomizer that takes advantage of this technology. And in doing so, when we looked at some Ti-6-4 studies, we actually were able to see what a free fall distribution would look like for Ti-6-4, seeing that the yields for both E-beam and laser cuts can be around 30%. And when we talk laser, it can actually be significantly less than 10% yield within the laser cut range. When you move to the closed coupled technology, you can really maximize that yield. And these are some size distributions that we were able to perform and look at here. And you can actually maintain it within the laser size range. As I said before, these are some experimental data that we've been willing to publish, and you can maintain around 70% yield when operating correctly. When we look then at our new facility, we really want to specify or really draw attention to that we operate a close-coupled titanium atomizer. Again, as I said, we practice the industry standard of induction skull melting. So that's using that water-cooled copper crucible. And this is a video down here that I hope will play so that you can see as we lower in our material, which in this case was a pre-alloyed ingot, it's melted in this water-cooled copper crucible. And how that works is as it melts, the liquid actually will splash against the side of the wall and it'll freeze, forming a thin little shell of titanium. You then use the induction or the electromagnetic field from our induction power supply to push the liquid off the wall a little bit, but therefore you're holding liquid titanium within a shell of titanium. This actually keeps the titanium very clean. Really, this is the cleanest melting process available, and as I said, it is the industry standard. We then look at transferring that liquid through the nozzle and using a pre-engineered gas structure. This is an example of the gas structure that we would use. And as you can see here, this is actually a photograph taken using the Schlieren technology, in which you can actually see the different incident and reflective shocks. And here is going to be your mock disk. Here, and so I want you to imagine that this mock disk actually exists in this image, because this is an image, or this is actually a video of close coupled gas atomization. And what's happening is the liquid's coming down, striking that mock disk. It's then being recirculated up here, wetting across the landing, sheared and driven down towards the supersonic core. And then it's going through that double stage, primary and secondary atomization. As you notice, it's momentarily chokes off the liquid stream, and then it starts again. And that's what it comes back to when we term this actually pulsatile atomization. When we look at it live time, this is close coupled gas atomization of titanium aluminide. This is the 4822 alloy. What we see here is that flickering. That flickering is real, and what's happening there is it's going through those two stages of flowing and then choked off, and so it's taking advantage again of that primary and secondary atomization. And controlling that pulsatile frequency is key to controlling the size distribution. Again, this is close coupled atomization of titanium, which we were very excited about bringing to the marketplace, because it does allow us to maximize the yield of that type of powder. This is a cross section of our titanium atomizer, in which you see where it melts here. It's driven down the large tower. We use high purity argon to drive the solidified particles to a collection vessel, in which we then collect the titanium after the run on each batch. Moving forward, we have some of the benefits here we want to talk about is superior economics. When you can take advantage of a system like this, you can move to large batch size, superior yields, and really high throughput. Throughput that allows you to melt and pour several 100,000 pounds of liquid titanium annually. This also offers you the flexibility to melt a lot of different variations of titanium, whether it's Ti-6-4, Ti-aluminide, or other custom alloys that's created from different type of elemental raw material. Processing titanium also offers unique safety challenges. You have to understand how to handle that titanium, mostly under a cover gas or using specialized equipment to keep it under argon, or you need to passivate that powder in situ. Therefore, you actually have the ability to coat those particles with a native film of nanometric oxide to prevent them from oxidizing when they're then at first exposed to air. That prevents them from heating up in air and prevents what we call thermal runaway if they do burn when first exposed to air. And so we do operate a world-class safety facility in which we do process all this material with very specialized equipment to handle it in the most safest way and within the NFPA standard. When we look at then, we have to have specialized and dedicated cells for making titanium powder, including sizing, blending, and packaging, to not only prevent any safety hazard or eliminate any safety hazard, but to also prevent any type of cross-contamination with other powders that we make in our facility. So we are very proud of this state-of-the-art facility, in which is really an improved source now for aerospace-grade powders. Part of our new titanium atomizer led to a partnership between Praxair and Buffalo Works, which is a division of EWI. When we look at this partnership, we're really excited about it because we could take some of our titanium powders, in particular titanium aluminide and Ti-64, and partner with EWI and Buffalo Manufacturing Works to develop print parameters. These print parameters can then be used with our customers. We can supply them to our customer base to really use our powder, drop it in, and start to print right away. What this allows is it cuts down on the development time. So when we're able to partner with people or with divisions or entities like Buffalo Manufacturing Works, it allows us to create these parameters that's perfect for our powder. So we can supply powder to the customers and the parameters to our customers so that they can start printing right away. And we can optimize those parameters so that we can improve build times, build part density, and really try different geometries. And some of these geometries were actually brought to us by our customers as a proof of concept. So can our powder be used to make these geometries moving forward? And so this is a very exciting partnership that we continue to work on today, and we do think it's a natural progression from powder to parts to commercialization, and we're excited to be part of it. We also operate on campus here our own additive manufacturing laboratory, and we offer this service for our customers as well. And so we use this laboratory, or we leverage this laboratory with our specialized atomization equipment. As I spoke to earlier, we do have a developmental atomizer that can produce smaller batches of gas atomized powders in custom chemistries. And so we can create with our customers a design of experiments to look at a variation of particle size ranges and chemistries. And in general, looking back over the last 12 months, we've probably made more than 2,000 custom alloys in this powder plant that can be then used in this type of equipment to really develop a most ideal alloy for printing. What we see, and we've done some case studies here that we've presented in the literature, is that there are easy to weld alloys that are available for additive manufacturing, and then there's very difficult alloys that have unique mechanical properties, but we don't have the print parameters available to really ramp that up and commercialize it quickly. And what we find out is that if we zero in on the key elements in there that are preventing these alloys from being printed, or in some cases resulting in cracks within the printed part, if we can figure that out with our customers, then we are able to actually scale up from our developmental atomizer to our pilot scale and then all the way to production scale. We've had great success there, moving from pouring 50 pounds all the way up to several thousand pounds of this material that is now being printed. And we were able to solve a key problem for several of our customers using our developmental technology. So again, this laboratory is really exciting for us, in which we can not only develop alloys specific for additive manufacturing, but also optimize the process and how they're printed, and really use that to our advantage in making the best and most ideal powder for additive manufacturing. We're always excited to partner with outside businesses and certainly customers to maximize the effectiveness of this additive manufacturing lab. Another exciting part of our powder plant is that we're able to research and evaluate a key economic issue with additive manufacturing, and that is, what do you do with the powder that you're not printing? So that powder that you've loaded your machine with powder, you print your parts, and after the fact, you're left over with a significant amount of powder. Is that powder waste? Can you recycle it? Can you reuse it? These are a lot of questions that we're getting from our customers. And so we're able to go into our laboratory and run a very well thought out design of experiments in which we printed a material. In this case, it was Hastex, and we printed it 10 times. And so we essentially were making these unique tensile bars. We were taking the leftover powder, putting it back in the machine, and printing again. So we made a series of 10 lots of powder, or 10 lots of parts from the same initial batch of powder. We then evaluated those parts using mechanical testing, and we saw really no drop-off in mechanical properties. And so the question is when is the powder out of its life? And can we reinvigorate that powder or recharge that powder using our powder plant in terms of, do we mix that used powder back in with virgin material to extend its life? How has the flow changed with time? How does the chemistry deviate? These are things that we still need to develop. It's very exciting for our customer because it allows them to really understand the limitation and understand what will they sacrifice given the long term, and it allows them to really study their powder specification and understand, can they increase the particle size distribution range within their original specification. And so we do think that this is going to be a key component to large volume production of additive manufacturing, and we are actively in this space. We're very active in this space, trying to find solutions for some of our key customers. That's for sure. But again, another way to take advantage of this synergy between our additive laboratory and our powder production facility. So with that, I really wanted to wrap up and allow time for questions at the end here. But when we think about Praxair, we want to understand that we do have a base of really a great volume of understanding when it comes to engineering gas atomizers and engineering structure. But that's one thing I want you to remember, is that when it comes to atomization, you really have to understand, how do you transfer that liquid metal through a nozzle and then interact that liquid with a pre-engineered gas structure. Those two things are very germane to the success of atomization and to the success and yield of powder for additive manufacturing. So we take advantage of key pieces of technology. In many cases, it's proprietary technology that we've developed and we produce internally. And we do have a plethora of experience of gas atomization, well over 50 years of understanding how to deal with gas, and we do lean on our parent company, which is Praxair, the gas company, which is one of the largest suppliers of industrial gas in the market today. And that synergistic relationship has been very beneficial as we expand into this new market. So with that, I'll open it up for questions, and I do thank you for your time.
Thanks, Joel. Very informative. We do have a few questions already from the audience, and we've got some time left at the end here. So if anybody wants to use that question panel on their control panel, go ahead and fire some questions at Joel. The first question, Joel, is what is the pore size of your titanium heats?
Okay, right now our heat size is approximately 200 pounds. And what we were able to develop there on our titanium atomizer is what we call the quick change technology. And so not only is it heat size, but for us it's throughput. So how quickly can we recharge that crucible and pour again? And so we're very excited about this quick change technology. So not only can we melt and pour about 200 pounds per heat, but we can do many of those heats every shift. And so that's what allows us to get to that large throughput of several 100,000 pounds of product at the end of the day.
Okay, next question is, you said that the crucible in the atomizer is water-cooled copper. Is the nozzle traditional ceramic or also water-cooled copper?
So So the nozzle is actually is made of a series of different materials. Those materials each have a specific purpose, that is insulating, that is heating, and that is for melt contact. And so that is a proprietary nozzle, and a lot of IP is built around it that we don't share exactly how it's made or what it's made of, but it is inert with the liquid, and it does allow us to pour those large batches and heat that liquid in situ as it's transferred from the crucible to the gas structure.
Okay. How do you ensure that the melts are homogeneous prior to pouring?
Well, that's a really great question, because as you see the complexity of additive manufacturing powders grow, you do see customers now asking for alloys that can have over 20 different elements in there, very tight chemistry distributions. And so as we add that, we have to use our engineering team to develop specific melt recipes for every alloy. And so our engineering division does spend a lot of time developing specific instructions for every heat. We go through how do we calculate that heat chemistry, then how do we load it into the crucible, and how do we make sure that the liquid is actually fully molten and therefore mixing. And so we first use theoretical software to calculate a melting temperature. We load all the components in a strategic way so that once it is liquid, then we raise the superheat level. So superheat means the amount of temperature above the melting point. Once it's molten, we do have a given amount of time that it's held in the molten form before pouring. And again, that comes from our recipe, and we use the electromagnetic field to create stirring within that pot. And as it's stirred, we believe that it achieves a homogeneous level. And after it's poured, we test every batch of powder for its chemistry. So we need to make sure that we go through lot inspection on every heat, and so that we can confirm that there is homogeneity between, within that lot when it is atomized. So that's a great question. It's something that you have to develop with your engineering team, and you have to balance with your experience level. Those that don't understand how to melt those complex alloys, it can be a real problem. You can see segregation if the melt temperature is not high enough, if you didn't melt in the correct order. So these are things that have to be well thought out, especially as this market grows and the alloys continue to grow in their complexity. So, yes, great question.
Very good, very good. Joel, again, tell us the quantity of titanium that you're atomizing per heat.
Per heat is 200 pounds.
200 pounds, that's what I thought, okay. And the typical duration of the heat?
For which atomizing?
How long does it take? Well, good question. He just says, what is the typical duration per heat?
So our metal flow rate is going to change based on what our target size distribution is going to be. We can be flowing anywhere from as little as 4 or 5 pounds per minute all the way up to 60, 70, 80 pounds per minute. So it really is dependent on what our customer specification is, what the physical characteristics are of our liquid metal. The liquid metal we have to look at surface tension, fluidity, and then size distribution. So it is dependent on the specification. We have to modify that, and how you change that is you change your orifice size in your nozzle as well as your gas structure. Are you creating more back pressure or less? How much suction do you run? In suction, we use the term aspiration. So what aspiration are you going to operate at? But you will change your liquid metal flow rate significantly by modifying your gas structure and your nozzle. And again, our engineers help us develop that for a given customer specification.
Okay. One of our attendees wants to know if they're going to be able to get a copy of the slides. I don't know how you feel about that. We will put the archived webinar, as I said, on our website so people can watch it.
Yeah, they can. And I would suggest, Brad, that they contact us at the email that's shown on the screen today, and we can talk with them about distributing the slides.
There you go. Okay. Thank you. Are there different powder characteristics for powder bed versus, I guess, direct?
Yeah.
For powder fed.
Yes, there certainly is. We look at different distributions. Powder fed, in general, think of it as slightly coarser powder, and in some cases, a little more narrowed size distribution. So when we talk about feeding, it's just a different technology, different flow characteristics, but the powder bed, in general, I'm going to speak in general terms because there are some outliers, but in general, powder bed has finer powder, typically less than 45 microns, and blown-in powder is slightly coarser. It can be somewhere around 90 or 75, all the way down to 45 microns. And then those are general rules to think of.
Okay. Okay. And then what do you do with the powders that don't meet the customer's required size range?
So powders that don't meet the customer size range, what we'll look at is what is the chemistry of those powders, what's the condition of them, and so we'll go through our QC lab again to evaluate. And then with those powders, we can actually classify them as revert, and they can be remelted in our atomizer. When those powders are remelted, it's important to understand that they are going in a pre-alloy condition, but they can also have slight amount of elevated contaminants like oxygen because of the high surface area. So you do have to understand and modify your melt recipe with that, and understand that you're going to create more slag. And so you have to just be aware of that, and your engineers need to be able to look at that and modify the melt chemistry appropriately. But those powders in general can be remelted under certain circumstances. So that's what we do with the most of them.
Okay. In terms of developing powders for AM, are you guys using a number of different OEM machines to help you develop those powder alloys?
We do. We typically will work with our customers on a case-by-case basis. Many of them will have their own machine that they want us to develop powder for, or they'll be using a third-party job shop, or they'll come on site and use our equipment. So on site, we do operate the EOS machine, but we do have access through several partnerships to different equipment. But in general, it's a case-by-case basis, and the customers kind of guide us on what machine they want to use, and then we start to develop additive powders for them specifically.
I see. Okay. So you mentioned weld powder materials. Can you talk about some of the most difficult weld powder materials that you've processed to develop parts, either in the lab or with your partners?
Some of the ones that have a more tendency to crack. Is that what you said? Weld powder? Is that
yeah,
right?
the weld powders that have been difficult to work with that you've successfly processed as AM parts.
Sure. And in many cases you see difficulties with Hastex. We're seeing that across the board, as well as some others, maybe Haynes 230, and then a lot of them actually are coming to us with proprietary alloys, maybe a derivative of Hastex, and then they're working with us to make them a series of alloys in which we're slightly tweaking the chemistry, printing them to give them feedback on the most ideal powders and the most ideal mechanical properties accompanied with those chemistry. But right now, if you look in the literature, there are quite some difficulties with Hastex that we're working through and trying to solve.
Okay. Do the powders meet some of the industry specifications, the NACE and the FDA, for example?
Sure. I mean, a lot of the specification, because additive is so new, customers really have their own internal specification that they want the powders to be made to. Of course, in general, some will look into the AMS standards and bring us a lot of the aerospace standards to start with, and then we'll tweak along the way. And you're even seeing many of them derive from previous wrought specs, and so specs that were written around castings and wrought material that are now being transferred to the powder world.
Okay. Question is, do you have figures for the electrical energy consumption per heat when producing titanium?
Sure.
Energy consumption by pound or what have you?
Yes, we certainly do, because of our we track the kilowatt hours per pound during every batch, but unfortunately, it's not something that we release publicly.
Okay. Do you want to talk a little bit about when you're changing alloys, how you prevent contamination?
Sure. So I showed some pictures of that large atomization equipment, and in general, we're making a high mix of powders in this plant, and so you really have to understand step one. Our plant ensures that safety is number one, and so we make sure that all of our operators understand the hazards when working with powders, making sure that they're adequately trained and properly equipped with PPE. We then want to make sure that obviously that quality is first in our plants. And so we have to prevent cross-contamination. So we actually go into those atomizers and clean every surface that's in there during changeovers of alloys. So we clean every surface. We have to disassemble the atomizer. We reassemble the atomizer, test it for vacuum. We then blow down the atomizer to make sure that no powder is then coming to the collection vessel. And in some rare cases, we do process the wash heat, and so that after cleaning, we do pour some liquid metal through that atomizer to act as basically a washant or some type of scrubbing material to basically coat the system with some powder of similar chemistry to prevent it from, or identical chemistry in many cases, to prevent any cross-contamination potential that might exist. But that's pretty rare. Mostly, we're pretty happy with the condition of that atomizer after cleaning it. So that's what we do. We have to go in and clean every surface.
Okay, good. So we're close to the top of the hour. We've got one more question. We maybe have time for one more after this one, and then we'll have to sign off. So the question is, does the shape of the powder affect the way it packs? Some of the powder bed machines compact the powder pretty well as it spreads a new layer. So you want to talk about the shape of the powder and how it affects the way it's compacted? Certainly.
I mean, when we look at packing density and spreadability, I mean, those two things are fairly well aligned. And when you talk about packing density, if you change your particle morphology from spherical to irregular or I guess faceted, you're really going to cut back on your apparent density, your tap density, and your pack density. And so you really can achieve the most highest level of pack density by moving to a spherical powder and then selecting the most optimum size distribution so that the smallest powders do have the ability to penetrate the interstitials between the larger particles, and that's how you maximize your packing density. When the powder is irregular and in many cases faceted, it creates quite a size distribution of interstitials between the particles. Therefore, you don't get the same effect of very fine particles filtering down and packing the interstitials between the large particles. And so that's one of the key factors that prevents high or controlled packing density when it comes to irregular powders. So really you can achieve the most ideal and repeatable results by using a spherical product.
Very good. Okay, and the last question will be, you said that the size or configuration of the atomizer chamber does not really impact powder morphology or powder size distribution. Is that correct? This person just wants to verify what you said. Okay.
Yes, in general, that's going to be your rule. And so when you look at that, you might have some slight different current or gas flow within very large chambers that you need to consider when designing. But in general, it doesn't matter how big a chamber you have when it comes to melting. It all depends on that nozzle and that gas structure. That's how you're really going to determine your powder shape, size, distribution, and surface characterization or surface morphology. So those are the things that you really have to zero in on. Of course, as you move to larger chambers and you can melt more, that's how you maximize your throughput and can achieve millions of pounds of throughput every year.
Okay, good. Well, thank you very much, Joel, for your presentation today and for a really great Q&A session as well. And I want to thank everyone for attending today's webinar. We hope you found it to be valuable. Again, please remember that an archive of the webinar will be available on the website of 3D Metal Printing Magazine very soon. we'll send you an email when it's there, and we'll give you a link so you can review it again and perhaps share it with others within your organization. So again, thank you for attending. Thanks to Joel. And you may close your browsers now. Everyone have a great afternoon. Thank you.
Thanks, Brad.